Functions of 2 or 3 variables are not the only things that we can integrate over a curve. In fact, they might not even be the most useful things to integrate over a curve. It turns out in a lot of applications, it is better to integrate a vector field over a curve. Remember, we introduced vector fields in the last set of videos. It's essentially a function, say f of xy or f of xyz, that takes that for every point in either the plane or three-dimensional space or some section in the plane or three-dimensional space, it assigns to each point a vector pointing in some direction. This is kind of the same as when we had little f of xy and little f of xyz, where it assigned a number at each point. Now we're assigning a vector. What we're going to do here is we're going to look at the physics concept of work and kind of give it an interpretation as an integral. So remember, work, if we have some force acting on an object that travels over some displacement vector d, we take the dot product of the force and the displacement vector, and we get the scalar that we call work. If force and displacement are in the same direction, then we're really just multiplying force times distance, but when we have different directions, we compensate by using the dot product and using vectors. What we want to do here is we want to generalize this idea by having the force be able to change as we move along some curve. So instead of d being we travel from point A to point B by a line, we instead use some curve to get from point A to point B, and the force can change along that curve as well. So let's go ahead and maybe draw a picture here. We have some curve called C. I'm going to go ahead and give it the vector valued function notation instead of using parameterized, making it a parameterized curve. And we want to see the total work that's done to the object as we move from this point over that point. Well, again, we kind of look on the small scale, kind of taking some little pieces of this and kind of looking what happens as we're going through that. Let's say on some little sub-interval here, we want to say what is the work that's done over this part. So we'll kind of estimate it based off this point here. We see that at that point the object is moving in that direction because it's following that curve. That's a tangent vector. The force may be some other direction. I don't know. Let's make the force this way. So this is the force at that point. This is the tangent vector. And we'll usually go ahead and use the unit tangent vector. We're approximating our displacement by that tangent vector. And it's, in essence, on this little piece here, we'll say the work is equal to the force at that point dotted with the unit tangent vector. And we're essentially we have this function. This is now a scalar function depending on these two vector functions that is going to be changing over the course of this curve. And we essentially want to add up the values of that scalar function. But once we have a scalar function, we can go ahead and treat that using the line integral that we talked about before. So essentially we use the original line integral to add up all the values of this f dot t over this curve. And we'll say that is the total work over that curve. But it turns out that this is not actually the easiest way to tackle it. We don't always want to have to find the unit tangent. But what we can do is we can write out what that unit tangent is. Recall that the unit tangent, we take the derivative of our function, of our vector valued function, and divide it by the magnitude. Essentially, the derivative is a tangent vector, but then we have to turn it into a unit tangent vector. If we go ahead and plug that into here, So let's say this is from t equals a to t equals b. So we're going from a to b. F here is actually f of r of t. We're dotting that with our unit tangent, which is r prime of t over the magnitude of r prime of t. And then when we're doing a line integral, remember we have to multiply by the magnitude of r prime of t. That's part of our formula. So we're essentially taking f dot t, but we're plugging in r prime, or sorry, we're plugging in r, but then we also get this extra square root of stuff attached to the end. But here, these magnitudes actually cancel each other out. We're dividing by that magnitude, we're multiplying by the magnitude. So really, we can just write this as f of r of t dotted with r prime of t. We are going to write that like this. So we're going to say the integral of f dot dr, so that's the notation that's been chosen for this, just kind of specify here that we are actually doing a dot product in here. That's going to be the integral of the function at r of t dotted with the derivative r. Or you can actually go back to the original integral of f dot, the unit tangent. But mostly we'll be using this as our way of actually evaluating stuff. Now actually a lot of the examples will actually be written in a little bit different form. So here, if we write r of t as a parametric curve, so we have some function for x, we have some function for y, and we have some function for z. Of course, if we're working in 2 dimensions, we wouldn't have the z part, but we'll make the obvious modifications for that. We can write out f. So here, f is our vector field, and remember we're taking f and splitting it up into components as p, q, r, or just p and q if we're working in 2 dimensions. If we do that, then the line integral of this is going to be the integral from a to b of, well, f is, remember, is just p, q, r, dotted with the derivative of r. Derivative r, so derivative of x with respect to t is dx dt. Derivative of y with respect to t, and derivative of z with respect to t. When we do this dot product, we end up getting p times dx dt plus q times dy dt plus r times dz dt. Now, since dx dt, that's really just dx. So we could write p dx dt as just p times dx. And the same kind of thing for y and z. So dy is dy dt times dt, and dz is dz dt times dt. So people like to write this as p dx plus q dy plus r dz. And that's exactly what they have in this box for us. Though they actually, I guess they changed back from a to b to going over the curve c. There we go. So most problems, well, some of the problems will be written in this different form. Some of the problems they'll give you the vector field and the curve. We want to be able to swap between them. Mostly I'll be taking things and putting them into this new form with the PQR. So let's see how this works in practice. We'll look on problem 8. Here we have the line integral over this curve of x squared dx plus y squared dy. So this, you kind of, sometimes you'll have to figure out exactly whether or not we are working in dx, working with vector fields versus working with scalar functions. Scalar functions will have a ds. The vector fields will have a dx, dy, dz. So here you can see what we have here is a vector field. F of xy is equal to x squared y squared, or x squared I plus y squared j. The curve C is the arc of the circle x squared plus y equals 4 from 2, 0 to 0, 2, but then we'll also follow by a line segment. So we actually have two pieces to this thing. Let's go ahead and plot this curve to see what's happening. Now, since we are only working with the quarter circle for the first part of it, I'm actually going to go ahead and use the curve rather than just typing in the equation, because I don't want the whole circle in there. That does mean that we are parameterizing it right away, and I'm using the sines and cosines that we were working with before, and that's going from 0 to 2 pi over 2, because we're going from the point 2, 0 to the point 0, 2. But then they also want us to go from 0, 2 to the point 4, 3. We're looking for that particular line segment. So the segment from B to C. That's our curve. Kind of has a nice sharp corner at B, but that's okay because we don't necessarily need to have a actual smooth curve. We only need to be piecewise smooth. This is actually made up of two different smooth curves. One part is an arc of a circle, the other part's a line segment. What we're going to have to do is take the integral over each piece separately and add the results together at the end. But that's okay anyways, because we're going to have to use different parameterizations for each piece in the first place. So I've already kind of given a parameterization for the quarter circle. I'm going to call that quarter circle C1. So maybe I'll even go ahead and label it in the picture. Well, let's show it. Yeah. I want to make sure it put the subscript in there. Let's zoom in here. There we go. And I'm going to call the line segment C2. For C1, I'm using the parameterization of x equals 2 cosine of t, y equals 2 sine t, and t is going from 0 to pi over 2. We need to go ahead and differentiate these things. So our dx, when we differentiate this with respect to t, we get a negative 2 sine t dt. You could write this as dx over dt if you want, but because we are going to be replacing dx with this thing in t, that's what we want to do. I find this makes a little bit more sense overall. dy, we're differentiating this one with respect to t. We get a 2 cosine dt. And now we essentially replace everything in here. Of course, we're not doing the full c yet. We're just doing c1. We're going to replace x's with the formulas in terms of x, dx with the formula for dx that we got over there. This is the integral from 0 to pi over 2. Of course, we have 2 cosine t squared times negative 2 sine t. Technically, you could put the dt here, but I'm just going to essentially factor out dt to the back. Then we have plus y squared. That's 2 sine t squared. dy gives us a 2 cosine t. And then the dt. And now it's just a matter of doing an integral. Of course, we actually do have, in both of these, we have 3 copies of 2. So we end up getting to pull out an 8. We have a negative sine t cosine squared t plus sine squared t cosine t. It actually turns out a little easier to do each piece of this individually. For this first one, I would make the substitution of u equals cosine. So du is negative sine. For this one, it's easier to do v equals sine, so that dv equals cosine. We do need to change our limits. So for u, when we plug in 0 and pi over 2 into cosine, we get a 1 and a 0. Remember to put the 8 on both pieces. For sine, when we say v equals sine, we go from 0 to 1. This first one, because we're integrating u squared from 1 to 0, we end up getting a negative 1/3. And then over here, we get a positive 1/3. So actually, those both cancel each other out. That's kind of interesting that we did get everything to cancel out. Why did that happen? Well, actually, it's not as unexpected as you might think it is. Let's think about what's happening to this curve. We're taking the dot product of this vector field and the tangent vectors to the curve. If we go ahead and actually plot all that, so let's go ahead and introduce a slider. And actually, I'm going to rename this to R, so I can use A for my slider. We're going to take this from 0 to pi over 2. I'm going to take a point on my semicircle based off of that parameterization. That allows me to move the point. If I want to look at the tangent vector at the point D, so I'm taking a vector starting at D and then moving from D by the unit tangent vector. Remember, our tangent vector is actually given by our derivative. So we had this parameterization for our curve. Our derivative is negative 2 sine t, 2 cosine t. Well, actually, when we want to do the unit, we actually end up getting rid of the 2. So our unit tangent vector here will be d plus negative sine of A, comma, cosine of A. So we have our tangent vector that's coming off there, and it follows our curve as we move around. Our vector field, on the other hand, so this is a vector, again, I'm going to start at D and move from D by what our vector field is doing. But what is our vector field doing? It's taking whatever we put in for x and squaring it, and put in whatever we put in for y and squaring it too. Remember, we're putting in these values here. So at these points, what we're actually seeing is the square of 2 cosine of t and the square of 2 sine of t. Oh, sorry. Not in terms of t. In terms of my slider variable a. So we have this vector that's sticking out over here. And as we move around, you might notice something kind of interesting. So at the extremes of 0 and pi over 2, and even at pi over 4, right in the middle there, these two vectors are perpendicular to each other. Between 0 and pi over 4, the angle between these is actually bigger than pi over 2, and between pi over 4 and pi over 2, the angle is actually smaller than pi over 2. But the angles over here kind of correspond to the same as over here. The dot products of things over here are going to be negative versions of the dot products that we have over here. So actually things cancel out very nicely between the first half of our arc versus the second half. So recall that what we're doing when we're integrating when we're doing a line integral of a vector field, we're looking at this dot product and seeing what happens to it. And so everything is canceling out with this dot product. And we're getting a 0. Now what about C2? Things aren't going to cancel out this time, but we can still do kind of the same thing. So here C2 is just a line segment. I've actually even given names to my points. I'm going to look at the vector from B to C. That's actually going to be the vector 4, 1. That's going to go ahead and give me parametric equations of x equals 4t and y equals 2 plus t. Remember there, I'm actually using the point 0, 2 as the first thing that we have there. Again, of course, when we differentiate, everything comes back to the 4, 1, but this time I'm going to write it as dx equals 4t and dy equals dt. That means when I do my integral over C2, remember we're integrating x squared dx plus y squared dy. The integral, well, I guess I should state up here that we are going from t equals 0 to 1. 0 gives me the point 0, 2. 1 gives me the point 4, 3. So we're integrating from 0 to 1. X squared is 4t squared. We're just using that formula. But now we're multiplying by 4 dt, so we have to multiply that by 4. Plus y squared. Y squared is, well, y is 2 plus t, so we have 2 plus t squared times dy, but dy is just dt. So we have dt here. We got to go ahead and expand everything out. Here we end up with a 16t squared, but times 4, so 64t squared. This expands out to be a 4 plus 4t plus t squared. So actually, our t squared actually is 65 times t squared. When we integrate 4, we get 4t. When we integrate 4t, we get 2t squared, and then the 65t t squared becomes a 65 over 3 t cubed. Still going from 0 to 1. When we plug in 0, we get 0. When we plug in 1, we end up getting 4 plus 2 plus 65 thirds. And so we get 83 thirds. We do the same kind of thing with our slider. Well, I actually have another slider, I guess. This one will be going from 0 to 1. We're going to go ahead and plot. Okay, well, I guess I unlike with the quarter circle, I don't have a function just plug it right into. So we'll plot the point 4b plus, or sorry, 4b and then 2 plus b, and that will be a point on the line segment. From that point, I guess I'll call it T2, or yeah, the tangent vector at that point is going to be E plus the vector. Remember, our vector was 4, 1. Technically, if I wanted to make this a unit vector, and I probably should, let's go ahead and divide 4, 1 by the magnitude of that. So that would be square root of 17. So we have our unit tangent vector. Well, you look at that. The point is constantly just moving along that line. It doesn't change direction. On the other hand, the actual force, not force, the actual vector field at this point. So we take the point E, and then we add the vector when we go ahead and plug in our 4t into, or sorry, 4a into t squared, or sorry, into x squared. Remember, our vector field is x squared y squared. Then we have 2 plus a squared. So that's actually quite a long distance up there. But as we move along, I messed that up. I put an A and it was supposed to be B. B is the one that's changing here for this one. There we go. So as we move along that line, the vectors are moving in this way. The actual vectors in the vector field are changing in that way. And we're integrating, or we're essentially adding up all of the dot products between these two. So we definitely always, because we always have an acute angle between the two vectors, we always have a positive value for that dot product. And because F2 is so long, we actually get some pretty big positive numbers. At least compared to what we were dealing with back on the quarter circle. And so that's why we got a value of 83 over 3. And then the whole thing over the entire curve was just add those together. We get 0 plus 83 over 3, or just 83 over 3. And so that is the line integral of essentially this vector field x squared y squared over that curve, and that's what we wanted to get. On problem 19, they give it to us as a vector field and a curve, a parameterized curve. They didn't give it to us in terms of the dx dy notation, but we can actually go ahead and do that. So here we can write this as the integral over c of xy squared dx, or that should be a minus x squared dy. So really, to change between the two notations, all you really do is take the I and j and replace them with dx and dy. Or if this was in our angle bracket notation, you'd have to change it kind of into this notation first. But we're doing the same kind of thing here. They've actually already given us our curve. We don't have to parameterize anything, and we can do it all in one piece. So here, remember, we do need to find what dx is. Here, x is t cubed, Actually, maybe I should write that out. Let me write out x is t cubed, y is t squared. That means dx is going to be 3t squared dt. dy is going to be 2t dt. I get to replace all my x's and y's with t's. T is going from 0 to 1, by the way. X is t cubed. Y is t squared. We square that. Dx gives me an extra 3t squared. I'm subtracting x squared, but x is t cubed. And that's squared. And then the dy gives me a 2t. I want to simplify all this, so what do we have here? We have a constant of 3, and then we have 3, 4, well, 3 and 4 more, and then 2 more. So we end up getting a total of 9 t's. Over here we saw the minus sign, we have a 2, and we end up having 7 t's. When we integrate that, well, it's 3 over 10 t to the 10th, minus 2 over 8, or 1 over 4, t to the 8th. When we plug in 0 again, everything becomes 0. When we plug in 1, we get a 3/10 minus 1/4. And that in total becomes a 1 over 20. Now, if we actually want to go ahead and plot this and see what's happening, so here recall that our curve was t cubed, t squared, where our parameter is t going from 0 to 1. So we got this little curve here. I'm going to go ahead and pick a slider here. Actually, I'm going to change the name of this to R. And make a slider from 0 to 1. I'm going to go ahead and plot a point on my curve. So R of A is a point that moves along my curve. I'm going to go ahead and take the unit tangent at that point. So remember, to take that unit tangent, I'm going to take A, then A plus the derivative. The derivative here is 3a squared 2a, but then I need to divide by the magnitude of that. So I'm going to square those. So we have 9a to the 4th plus 4a squared. Now, if I did it right now, actually things would kind of mess up if a equals 0. So actually, I'm going to go ahead and pull out an a squared from inside the square root, and that will cancel an a on the top. So just kind of bear with that. If you want to work it out directly, go ahead. And what? Why don't you like that? I giving you the point A. Oh, because I didn't put want to put vector. There. Okay. Don't neglect to put the name of the function that you're using here. Okay. So we have a unit tangent t that's following our curve. Kind of looks a little off at 0, but that's just because it does get actually really vertical there. Now, what is actually happening to the actual vector field? So recall, we have a vector field that's equal to xy squared comma negative x squared, or I guess right up here. We have xy squared and we have minus x squared. I'm going to take the point on my curve and I'm going to give it the vector of our vector field at that point. So a comma a plus, so xy squared, so x is t cubed, y squared is t squared squared. In other words, we have 7 t's in there. And then we have x squared, or, well, sorry, negative x squared. So we have minus x is t cubed, so we square that, we get t to the 6th. And again, I need to switch to a. And it's saying 0, 0. It's not technically 0, 0 here. It's only going to be 0, 0 at the origin. As we move away, it's just so small that you can't really tell what's happening. You're plugging in very small numbers into a to the 7th and a to the 6th. As you get further away, it finally actually shows something, but you still can't really see it. But as you get further out, it actually gets bigger and bigger. So very small, but then it gets bigger and bigger. And technically here, these are never actually, well, I guess they're definitely orthogonal at 0, but they're not orthogonal as we go out. There is a little hint of an angle here. That's not a right angle. So we're not adding up zeros or anything like that. But since they are very close to being orthogonal, and f is really small for a lot of the curve, that's why we get a number as small as 1/20th. Okay, for our last example, we're going to do problem 22. This is very similar to what we did in the last problem. Here we have a vector field, we have a parameterized curve. You can write this as x equals cosine of t, y equals sine t, but this time we have a z involved as well. Z equals t. The line integral of f dot dr, or in other words, we can say the integral of x dx plus y dy plus xy dz. We do need to know what dx, dy, and dz are. Derivative of x with respect to t is going to be negative sine of t, dt. Derivative of sine is going to be cosine t, dt. And then, of course, the derivative of z is just going to be dt. We go ahead and plug everything in. Again, the t is going from 0 to pi. X is cosine. Dx gives a negative sine. Y is sine. And then dy gives a cosine. And then xy, we have a cosine and a sine. I'll put the sine first. But the dz just gives a dt. Now, one thing we can do right away, notice that we have a product of sine and cosine, product of sine and cosine, but one of them is negative, so we'll cancel those out. I mean, technically, we still have a product of sine and cosine. I'm going to go ahead and make a substitution. I'm going to let u equal sine of t. So the du is cosine of t dt. For sine, we're going from 0 to pi. Well, we get a u du, by the way. But when we plug in 0 and pi into sine, we get 0 for 0. And we get 0 for pi as well. So here, everything's going to be 0. We didn't actually integrate over any non-zero interval. So we got 0 overall. Let's go ahead and actually plot this thing. Now we are working here in 3 dimensions. Our curve is 3-dimensional. Remember the parameterization of the curve is cosine sine t, variables t, and it's going from 0 to pi. This is another well, it's basically the helix that we had before, but now we're going halfway around the z-axis. I'll go ahead and add the unit tangent and the force and the vector field. So here I've plotted point A on the curve. We have the unit tangent t coming off here, and we have the vector f. That's from our vector field. As we move that around, well, it starts off orthogonal. Those are definitely perpendicular to each other. As we move away a little bit, that's not actually orthogonal anymore. It's actually an acute angle. As we get to pi over 2, they actually become orthogonal again. It's a little hard to really see it directly. And then it becomes an obtuse angle before eventually becoming orthogonal again. So kind of what we have the same kind of situation that we had in our first example, or at least for the first half of the first example, where on part of it we have positive dot products, and on the other part we have negative dot products, and so they end up canceling each other out. Alright, but as you can kind of tell here, the actual work involved is actually not that bad. Once you can identify the parameterization for your curve, you just kind of plug things in and work it out. All the actual graphing that we did was not really necessary in order to even understand what was going on. It's just trying to get a grasp on what this means geometrically. In the next section, we will actually talk about specific kinds of vector fields and see how those actually are related to the line integral. And moving on to the section after that, we'll actually give another interpretation of what line integrals mean. But we'll get to that as we go. So meet me in the next section in a day or two.